for optimization for deep learning algorithms. So I'll try to combine two, two, three, two, three thoughts and presentations so that we can really get excited that why this is important then and how people are moving in that direction. So the thing is, we start from here. Mostly when we talk about deep learning, let's build the whole story from the very small models, and that is basically a neural network. So what is there or machine learning models? So mostly we are given with some inputs, maybe in binary form, or maybe some images, or maybe some signals, and then there is some expected output that this has to be output. And what we want is we want a model which map input and output. That is actually what is AI all about. Uh, and that's the difference between your AI and your computer programs. In programming, what we do is basically we give the relation, we give the model and give the input, and then the algorithm give us the output. But what we are doing here is we are giving the input, and then we raise the question that give the model which will give us this output. So that is the job there. And when we talk about the model, that means there is certain kind of a mapping between the input and outputs. And depending upon the model, depending upon the complexity of the data, the model is being designed. That's the whole in AI. So if this is the input and then somebody asks you, okay, give me the model for it, and let's talk about neural network. So we are going for a neural network. So neural network, we give the inputs, which you can see here. Let me take a pointer. So we have inputs, and then there is certain kind of a mapping. Mapping is done by some kind of a weights, okay, and then we sum those. It's a linear aggregation, and then we put a nonlinear function here to generate the output. That is actually happen in neural network. So neural network is a weighted sum, linear sum, and then we pass it through a function, which is usually a nonlinear, because the map because if my data patterns are nonlinear, if they are linear, then you can use it a linear function, and then we have an output there. Well, in that case, the question is how we get these weights. Okay, how we will get these weights, and to get these weights, what we do is we initially start with the random weights, and then we generate certain output, and then we check that output, that what has to be the actual output, because we know that this is the actual output. So then we calculate the error, and then we develop a loss function, and then develop a mathematics that minimize this loss function. So the time I'll say minimize this loss function, that means I'm converting this AI problem to an optimization problem, because we are minimizing the loss function. Now, if I'm saying that minimize the loss function, then we have to see that what are my variables. Now, obviously, my variables are, if I take now this is the point where we have to think of. If I take my variables only the weights, these weights like one written here, fine. Then my optimization problem is minimize the loss function subs with these variables, and I can constrain my weights also, and then I solve it. Now, there are various ways to solve it. So one way is basically, which is very popular, very common, and that is back propagation. So that is basically inspired from our chain rule, which most of you are aware of because you are mathematicians. And what we do is we calculate the error at the outside, at the terminal, and then back propagate the error and keep on updating, because we know in the chain rule that this is the way we can do it. Well, now this is the start of the optimization, and if we know that everything which is there in this path from output towards this side going back, if it is differentiable, then we can go by the classical we can go by the differential approach, and we keep on finding the derivative and keep on moving back. Now for that, the condition is here. For that, there is a condition, and the condition here is this function, which nonlinear function you are going to use in this box, it has to be differentiable. But if it is not differentiable, then things stops here. Then we have to find out an alternate solution. Well, this is the way neural network we do in neural update the weights, but we find the optimal or best updates so that the error or loss function is minimized at the output. Well, this is a simple case, but when we have complex data, then our network size changes. We have to introduce some in between layers. Those are known as hidden layers. So this one is a neural network, and we earlier we don't have a hidden layer. Now we are introducing hidden layer because our data patterns are in such a way that we need multiple decision boundaries so that we can separate them or identify the things there. Each layer is a certain, you can take it generate a one decision boundary. But if my data are very complex, I have to go for multi-layers. Now, if I'm going for multi-layer, now the complexity further increases because it calculates error here and then moves back, update this one, then moves back, update this one, moves this side. So it update weights everywhere. Now the complexity increases. And in any scenario, if the things are if in any case the things are non-differentiable, then complexity increases. Otherwise, we can take the derivatives and then keep on updating the things. Now, when you are taking a derivative, it's fine, but just think of it when you implement into the programming part, each derivative has an impact there. It creates certain kind of computational complexity. More derivatives, it introduce more big, and then there are certain kind of certain complexity attached with it when processing all these things back in the backward direction, and then people come and that because of that the training, this we call as a training is nothing but updating the weights. So the training becomes slow, then people come out with some accelerated gradient and more on those things. Probably Dr. Priyanka will talk more on that. I think she has already discussed on these things, but this is what is happening there. Whereas in this whole till so far, what we are discussing is updating these weights and all these things. Now my problem is more complex. I want to recognize this face. Well, let's make it simple. The initial stage, how people did it. What they have done is they have divide this whole image into some inputs like nose, eyes, left eye, right eye, lips, ear, left ear, right ear, and likewise. And then develop a multi-layer network to identify whether it's a face or not face. Well, now the complexity increases because now we have taken these things as inputs. These we call as features. So we have done some feature engineering here to find out these features and then pass it to the input layer, then the hidden layers and the output layers. And again, the weights of these all these connections, they are updated through optimization process. If my everything is continuous, I can go for gradient based approaches and all that. So then and this is how we will get these values, then all these values. So this one is an iterative process. Initialize, because what we want computer to do it. So we just pass the mathematics in such a way that okay, follow these guidelines. So it's a kind of a weight update mechanism. It's a gradient based weight update mechanism. It's iterative in nature. So every iteration it keep on running and updating till we'll get the minimum error at the end. Well, this works fine, and then people later propose it few more things because now my problem become more complex and I'm going for this. Okay, so they say no, this is the feature engineering part for images, you are good in it, so then you can easily find out what is nose and all these things, and then you find out these features and then pass it. But For a person who is not an expert of that particular domain, may not able to do good feature engineering, and that's why the error will be more. Then why not to have a network which itself do the feature engineering? So then people come with a long network like this. Okay, it's a long. So initially people, if you go into the literature, early stages, they talk about the fat network, but later on they move towards the deep networks, the long one, this one. So what it is doing? So actually what it is doing, it is taking the pictures as it is, and then neural network itself generate features. And then, so you can see layer wise, if you break it into some layer, after some time it will get the patterns of the local contrast. After certain layers, you will find that if you see the output, it will be a face features. And then after some point, you can say, oh, it's recognizing the faces. And the last layer is basically giving the certain kind of output. So what is the advantage of making this structure? The advantage of making this structure is now it is independent of feature engineering. You just give the image, it will do the whole thing. So the process is automated. But what is the problem? The problem is you can see now to see the connections between the neurons. And for each update, you have to find out a derivative. And the chain of the derivative is very big now. So the training and all these things take a lot of time, and likewise. And that's why the optimization become a very important in deep networks or neural networks. So you will find a lot of variations. People talk about uh, if you talk about gradient based approach, they have developed many there. Simple gradient, batch gradient, momentum gradient, accelerated gradient, and then other different methods of optimization. Well, this is one kind of a flow. Okay, one kind of a flow means here some people tried meta-heuristic algorithms. So in the second half of my presentation, I'll talk more on that. So what they do is they say that, okay, this is one of the approach. What you are talking about, okay, we have a gradient and back propagation. Can we do it in another way? The another way they tried meta-heuristic algorithms also. They said that, okay, what we can do is all these things are fixed. You can see neurons and everything. Only weights are the variables. And then they applied like genetic algorithm, particle swarm optimization, and all those things to find out the solution. So then how the algorithm will work? The process is very simple. All these weights of this layer, weight of this layer, weight of this layer, that make a one gene. If I'm talking, let's say genetic algorithm, so that will be one gene. Likewise, there are 30 genes. And then what they do is they pass the values of one gene here, calculate what is the answer. Then pass the second one, calculate what is the error. Pass the third one. How they select it? Initially, they select it initially randomly. And then out of those, then they consider which are most fit. They keep those. And then they go for crossover and mutation. I'll talk on that one. And then they keep on doing all these stuffs. So what they are doing is they are putting this neural network inside a genetic algorithm for the update of these weights. The same this process, this type of pattern is applicable for all, whether it's a genetic algorithm, particle swarm, ant colony, or your grave wolf, whatever you can think of, meta-heuristic, you can put it. So that is one way, but yeah, just for this one, because we know that it's a gradient, it's a continuous, because we know what is the structure we have taken. And if it is a differentiable, then it's not a good idea, because these meta-heuristic take a lot of time, and all those issues are there. We will discuss when we talk about the algorithm part, but this is one of the structure. Now we are changing the complexity. The same optimization, what we are talking about is, no, we are okay, we will update the weight because we are doing the optimization. So if we are updating the weight, then my optimization problem is minimize my loss function, and the variables are the weights. Now I change the variable also. I put along with the weights, I put the hyperparameters also, like learning rate. Okay, that is one hyperparameter. Or I put a regularization to stop overfitting and all those underfitting issues. So when you put those things into it, or you put a architecture also. Architecture means how many layers, that is also a variable, and how many neurons in each layer, that is also a variable. So now my problem become very complex. Just think, how many layers, it's a discrete number. Okay, how many neurons is also a discrete. Regularization is a fraction values. Learning rate is also in fraction, but it is usually a very small number to maximum 1. And then your weights are also there. Now your problem become more complex. There is it's no more like a simple problem like in earlier case. But the point is, in earlier case we fix this structure that okay, 3 here, 3 here, 2 here, 3 here, 2 here, and likewise, and we assume all are connected, and then we use any kind of optimization, commonly used derivative, to find out these values. But now I change the whole problem. The problem is minimize my loss function, but my variables are number 1, number of input layers, number 2, number of neurons in each layer, number 3, my learning rate, number 4, the regularization, number 5, connections, skip connections, so that brings a sparsity. Then number 7, the weight updates, and the things become more complex. Well, then you have to analyze it, whether it can be solved with a differential approach or non-differential approach or likewise, and accordingly you have to choose what is your optimization algorithm. Now the good part here is everything is now done by the optimizer. You need not to check out how many layers and all those things. Optimizer automatically take care. It initially start with any kind of a random configuration, and it keep on modifying the configuration, weights, learning rate, and all those things. But and after some time, it will give you the most optimal structure for your problem. Okay, so that's a whole setup right now here. That what is the how the workflows there. Workflow like this. So they have this. I have few of these slides I have taken from the research article. So you will find different algorithms. In earlier slide, it was genetic algorithm. Now it's a grasshopper algorithm. Later on, you will find a gray wolf or bee algorithm or anything. We'll talk quickly on those things also. But what it will do is, we have data. It splits into test data and the training data. It take a training data and then initialize the network with some random value of the variables, and then pass the training data to that network, find out the fitness, and based on the fitness, then it follow a policy to update it, and this keep on running till we'll get the minimum error, and whatever the output of that network, that will be the best design network for you. This one is only for simple neural networks or MLP networks there. Well, now what is happening? We know that this is what is there. This is what happened in deep neural network. So we pass a maze, and then hidden layers, they automatically find out edges or features and then give the output. And then people keep on increasing these layers. This one is a CNN. We will talk more about CNN in the CNN lecture, but you take it like that. We take an input and there is one layer which do the convolution purpose. There is another layer which do the pooling, then convolution, then pooling, and there are multiple layers like this. And then finally we have a connected network to give the solution. At each point, each wire, you can see there are some operations. Operations means there are some weights, and that weight has to be optimally calculated to get the best results out. like this. You can see images here, 227 plus 227, and some part is basically feature extraction, some part is the classification. This is basically LXNet model. So you can see that how many layers are there. We'll talk about these layers when we talk more about CNN, but you can think of like the number is quite big, and it take a lot of efforts to find out these weights. Like here, this one is a zoomed one. So you can see input layer, then you can say there is a CNN layer. There are 32 filters, and the kernel is 2 cross 2, then normalization layer, pooling layer, dropout layer, and then the repetition of this again, then pattern layer, then dense layer, then dropout layer, then output layer. And if you see the configurations of a deep neural network, this thing keep on repeating. People are making just combination of these building blocks. Okay, so they are using these I'll show you one picture like this. You can see those blocks here, convolution, again convolution, and then parallelizing it to convolution with one max pooling layer. Now each block, there are connections, there are weights, and we have to find out the most optimal weight. That is the training. So you can see now you can think of the complexity of this problem. How many weights we have to correct. This is one part of it. If you go into this one is another one. Yeah, inception kind of a structure there. You can see the each block is like this, and there are so many blocks. In CNN, I'll show you the exact number and figures there, but we can take it from here that this is very complex thing, and this is one part, weights and all this. Another complexity is there, that how to arrange these things. Okay, so yeah, these are just to show you that how they are taking place. This one is Google Net architecture. So these modules, you'll see each module, this yellow block and then green and blue block, red block, they are placed in a different fashion. Like you can see here, you can see yellow they are parallelized, and here then they are in sequence. When you are doing, there are two green blocks and all these things. Okay, so this one like ResNet and all these things. And why people are doing all these combinations? All these are the different modules. Okay, so they are looking for all these things because everybody is looking for accuracy. But you see that then how many how many weights they have to update it, how many operations. So this direction is operations. You can see 155 million operations. And on this side, you can see accuracy. So if we go for more complex models, yeah, we have better accuracies, no doubt about it. But then the operation increases. So the quest is always is towards that, how to reduce the number of operations and how to increase the accuracy. And that is actually what is going on all around. But if you are an expert of this domain, now what is the another challenge I'm taking out, why this problem is more complicated? If you are a expert of this domain, then you can easily design that what should be the size. This one is okay input, but what is the size of this block? What should be the size of this block? How many such blocks are required? How many they are required in a series? How many they are required in a parallel, so that you have most accurate answer. But most of the people, they are not a designers. They are not like experts of those things. And again, this structure and all these things vary with the images also, with the data patterns. So what is the way to get it? Because this is a challenge, whether I should follow this pipeline, like okay, input, then this blue layer, then yellow layer, and then blue and the brown likewise, or should I go for this pipeline? Which one is good for me? So if I say we should try, then there are n number of combinations, and that my problem become very big, very complicated, because I cannot search all those things. So then again, then people come out with this idea, because They computer scientists, they implement, they tried, and they find out, oh, this one is a complicated. Then mathematicians, they jump into it. They say, no, no, let's make it another optimization problem. Why not we make it also a variable in optimization problem, so that the optimizer give us the most optimal structure. And that is really a challenge in deep learning algorithms like this one. This one is ResNet architecture. Okay, so what they say that, okay, uh, now it's your design. Now that this neural this optimizer can do can provide you a solution. Earlier they tried it like this. They put some blocks, like 4 block of this, 4 of this, 4 of this. They say no, the results are not good. Then they search it out, check it, where is the problem. They say that no, if I put more filters, my image information is lost, that's why I'm getting a error there. Then say no, suggest no, let's go for skip connections like this, and then those skip connections give a bit better results. But then the question is, how many skip connections, and then how many layers to be skipped? So those issues were there. And then as a, as a simple programming person, or there are various and number of solutions for, even if I talk about ResNet. I don't know how many layers should be there. I just keep on trying, hit and trial and hit and trial. It's not a never ending kind of stuff there, because the size of this block here, they are using 3 cross 3, and they are using 64. Why 3 cross 3? It can be 2 cross 2, it can be 5 cross 5, it can be 7 cross 7. Instead of 64, it can be any number. And then this block, there can be 2 block or 3 block or 4 or 5 or 6. And then there is another block layer, then another block layer, and then how many such block layers, and then how many such skip connections. So it's become very complicated. And here our optimization process helps us a lot. So they did various ways, they apply in various structures, and then they come out with these things there. So now let's summarize this thing before we move into the optimization algorithms. Yeah, just let me know how much time left, because of the time zone. Sometimes I miss the things. How much time we have more? Can anybody suggest me? Just me check it then. Okay, it will up to 130. Okay, fine. Okay, again we have 45 minutes. That's a good idea. So if I summarize it, we have to check it, because what is required when I'm designing a neural network. Now we are moving to that part. So the designing is, we need to see how many iterations are good enough, because we know that if I take less number of epoch, and then check it, it's possible that my network is not converse, means my loss function is not converse, it is still decreasing. And it may be possible if I take too large epoch, okay, it may be possible that at 500 epoch are sufficient enough. After that, it become a constant. So what is the optimal number of epoch? Then what is the batch size, optimal batch size? How many data in one batch should I send? What should be my learning rate? What should be my regularization parameters? What should be my type of layers, like fully connected or partially connected or LSTM layers or pooling layers? Then how many layers are there? Then how many neurons in each layer? How many filters? What should be the kernel size? What should be the filter size? So, now if my problem statement is like this, I have to consider each and everything. I need some kind of a complex models and complex those things there. Okay, so this is a structure. You can check it. This is just what we have discussed so far. The same thing I put it here. You can see these numbers and the parameters and all these things. They are very complex, and we need some methods to address it. there are various ways people are trying to address it. One way is your traditional way, and the second one is they are using a transfer learning approach. So they say that, okay, some part of model, the model is already trained on, say I'm working on some images, particular type of images, say X-rays. So there are models which are available, which are trained on uh, millions and millions of images. And then they say that, okay, what if they are trained, that means they are good in feature extraction. So what you can take it, you take some part of it, or you take more part of it and do the change at the last part. So if we do that one, then we can reduce our complexity, because we are training only the last few part where the classification is occurring. Rest part, feature extraction and all these things, we are taking as it is from the existing model. This approach is known as your knowledge transfer. So we are transferring that knowledge of the earlier models for our purpose. Well, it works fine. It makes the things easily doable on simple machines. You don't need very high processing units and all that. But still, people are struggling with higher accuracy and all that. Then, because the controller parameters are very large. And then another domain buildup, which is known as neural architecture search. This is basically complete design of the neural network, is NAS. It is nothing but it's a designing a neural network, but the main job is the job of the optimization algorithms, that how to build this one. So this one is again like all these which are cross, all these are the solutions of solutions generated by a PSO or genetic algorithm or any other approach. And you can see that who is the best, you can keep that one and you can kill the rest of them. There are various ways to do it. Okay, so the same thing which we have discussed so far, they also call it the auto ML. Okay, auto ML is again that your machine learning or your AI model is automatically designed, because it is considering everything. You have to do nothing. You just send an image and say this is a boy. Rest part is done by the this kind of a structure, because it automatically do the pre-processing, it do the feature engineering, it do take out the feature itself, it automatically find out the optimal hyperparameters, do the training, do the analysis, and give you final answer that okay, this is the final answer there. But again, the important part is we need to understand the landscape, because the landscape gives us the idea. Let's understand what is the landscape. Landscape means how many variables are there, and what is the nature of the variable, what is the complexity of my problem, because that will decide what type of algorithm you are going to use. Okay, so if your landscape is very complex, you need more complex algorithm. If your landscape is simple, or you can do some kind of processing on the landscape, then you can use simple optimization methods to design your structure there. There are various ways people have developed, like to perform all these things, like reinforcement, differential architecture search, one shot, training free methods, neuro evolution, and all that. All those are improvisations on the approaches. Since this is more towards optimization, so we I take I stop this part of presentation here, and we'll talk more about now optimization, other optimization methods which people are using. But you can take it like this from this slide, last slide, that if I restrict my layers, so layers like fully connected, CNN, LSTM, how many, and all those things. So if I restrict it like, okay, I will take only the CNN layer, one layer, and one fully connected. So I have simplified my search space landscape. Then layers also I fixed it. Neurons also I reduce it, that okay, I can go maximum up to 16 neurons each layer or something like that. Okay, dropout ratio I fix it somewhere near around. Okay, filters if I fix it, kernel size I fix it. I make my landscape or my search space, simple one, then I can go for a simple model. But if I open it up, I make it big, I have to go for more complex models. This is basically AutoML, what AutoML actually does, and then how you can design everything there. So now I think you're able to understand the complexity or a domain, that how important is optimization for deep learning models. Let's move towards the optimization part. So what I'll do is I'll change this presentation. I'll start with another presentation about the algorithm part. We'll talk about a few of the things here. Some of the methods, more towards modes are metaheuristic, because of the nature. If I'm going for a very most complex structure, where my problem is no more a simple differential kind or continuous kind of problem. My problem is an NP hard type of problem, where the combinations matters. And we know that if there are combinations and all these things, unless until you modify your problem statement, it's difficult to solve. So now everybody knows what is why optimization. So I just skip this slides quickly. And where is the problem in gradient? We know that now. Okay, so I'll just skip that part, because these are some benchmark problem. Now you see these benchmark problems here, the gradient will stuck up, it will fail. You see, if I take the first figure here, the minima is here. And if I start from this side, the gradient is already 0. You can see flattened space. It will not search, it will never reach here. It's stuck up there. Similarly, if I'm working here, oh, you can see there are so many peaks there. Like here also, so many peaks are there. So at peak point, that is already minima, and then gradient stuck up here. So most of the time, if these are such type of surfaces are there, my gradient will trap in local minima, local solution. Whereas I'm looking for the global one. I'm looking the best one. Local means, okay, it's a best, but in a very restricted zone. It's not the best in the whole of the space. And it occurs because of the property. So it's that, and that's the property of the differential approaches. Basically, they stuck up unless until you apply some operation over this surface and convert this surface in such a way that there is only one minima which is here. So those things are different zone. That is, I leave it for the mathematicians. They do it. They smoothen the surface, and then they do some kind of surrogacy and all those approaches. But as such, it's difficult. So people move towards search-based approaches or non-differential based approaches. So search-based are not very new. They are very old approaches, like linear search, which is basically searching in a linear direction. And in a way, what we have done in very early school days, when we try to find out the solution of a simple third order equation or likewise, we do hit and trial kind of. So that is basically same kind of stuff there. We try to find out the solution at the two extreme points, and then we reduce it and try to reach near to the solution. So that kind of mechanism is here. So you can see at the bottom, it is low, the complexity is low. So we have linear search, we can have a brute force search, we can have grid search. This is very popular. You can see the grid search is already inbuilt in many of the tools used for neural network training and all that. So this is grid search. So you are here, and then you assume a step size. You search at this point, you assume a step size, that okay, this is my step size. You add it to it, you reach to a new point, and then you search it again, and then you complete it, and then find out where is the best solution. So there's no any kind of a gradient and all these things appear here. Okay, so this is a low complexity, and then we can have a medium. Like then there are issues. Should I go like this or should I go like this? So if I go like this is a breadth first search. It has its own benefit, own advantage and disadvantage. and then there is a depth first. So we go searching here. So only the thing is the argument between the two, which one is better and which one is not. They say that if the solution is here, if you are searching like this, if the solution is here, you reach fast. And the counter argument is, if the solution is here, then what you have to do? If the solution is B, you have to search whole across first line, second line, third line, then you reach it here. So if you go by breadth wise, then you go search here and then you search here. So this one is better. So these are the arguments, and that's how people develop one method and then another method, and likewise. So this one is there, and then we have moderate setup there, where we talk about iterative deepening search or uniform cost search methods, and then best first search, beam search. All these are the search method. And then one of the most popular, that is A star search. Usually most of the people who are working in robotics, motion planning and all that, they use this method. This is very popular there, that is A star search. And then Monte Carlo, talking about more of the random and progressions and all that. So they have more complexity. These are the simple search based methods. And then people try to find it out, uh, different ways to search. So some of them interesting are there. This one is known as crime scene search methods and patterns. So if this is your search space, so they search it like this. Okay, this is one way of searching. The second way of searching is you go straight, finish, and then come again here, go straight and finish, come here, go. This is lane mechanism. This is a spiral search. You start and in the search in form of a spiral. You can search in form of a trajectory like this. You can search in terms of grid, or you divide your whole search space into zone and search in zone. In each zone, you can follow any kind of these methods. So this is one way of doing the thing. This one is again moving from one to another, but you can correlate it now with the gradient. It's a kind of you are here, okay, then you go for the gradient, ascent or descent, and then you go to the next and go to the next, and you reach at certain point. That is also, if you put a gradient into a iterative form, it's a way of searching the things there. Okay, so this one is one way of gradient. This can be the accelerated gradient. You can move in that particular direction, or momentum gradient. So these are the different gradient movement techniques you can apply. Okay, these are just a representation that how it move and the reach to the, this we already know, studied in class 10th. This one, somewhere we start with our optimization initials. Most I think everybody starts optimization from here. That is linear programming problem. So we have a linear objective function and linear constraints. So we draw the straight lines, and then we find out the corner points, and then we evaluate at the corner points, and then we'll say that which one is the most optimal one. Okay, so this is the feasible region. Meaning is all the points in this region, they are the solutions, but we have to find out the best one. So best one is usually at the corner. There are theorem which prove that in linear space, linear problems, the corner points are the optimal points there. And then people have applied certain kind of other mechanism like golden search or Fibonacci search method. So there are a lot of search methods, and they evaluate at the extreme points, and then they reduce the space by adopting certain kind of methodology. Then they search at the two endpoints, and then they reduce it and finally reach to the optimal solution. All these are in one or another way, they are searching with certain kind of interesting approaches there. And that is basically something is common here. And what is the common here is, that is basically next slide I'm going to put it. Common everywhere is there is a starting point. You can see here, this one is starting from here, this one is starting from here. In linear programming, we know that we start from 0 0, and then here also we start at corner points. Here we have starting point, here also we are starting. So there is a starting point. That is the first property which is common in all these things. You take any optimization problem, if you are working towards an iterative way of solving it, there is a starting point. The second thing is, there is a policy to move. Like, here is the policy. Policy is I start and then I move like this, and then I'll take a turn, move like this. This is a policy. Here is also a policy. Here is a policy that I'll move in a spiral form. Here is a policy that I move from this point to next point by taking the gradient, which is here. Here is a policy that I move to this point to the next point by momentum added to a gradient. Here is again a policy that I move from this point to the next point by some gradient. Here the policy that okay, we start from 0 0 and we take the neighboring point, corner point. Same is here. So that is the second thing which is common in all the algorithms, that they have a policy. And the third one is the last one. Third property which is common from all these things is there is a stopping method. So the most of the time stopping method, here the stopping method is if you complete the whole surface, stop. The stopping method here is if you reach a certain point, stop. The stopping method here is if the gradient becomes 0, stop. The stopping method in linear programming is if you check all the corner points, stop, and likewise. So this one is basically here. This one is a structure of optimization problem. I've taken it from a research article. Forget to mention the reference. Apology for that. But you can take it from here. There is few common things. There's a starting point. You can start randomly, or starting point is given to you, or you can develop another level of methodology to start your problem. Then there is a policy to update your position. It can be a gradient, it can be a momentum, it can be a neural network, it can be nature inspired, it can be a bio inspired, or anything like that. And then you update your position, and then there is a stopping criteria, how to stop your algorithm. This is how these things work. So why we are going for meta heuristic? Yeah, if we go by the conventional, it will take a lot of time. It's stuck up in certain kind of uh, solutions which are not not optimal. That's why people go for meta heuristic. So let's move into that, not wasting much of the time here. There are two common types of meta heuristic. We can divide them basically. That's a division basically we can talk about. So those are trajectory based and the population based. And then if you talk about them, we can categorize them like inspired from the nature, genetic, ant colony, cuckoo search, gray wolf, ant iron, firefly, and all these things. They are non-nature based, basically taboo search, okay, iterative local search methods, and likewise. We have objective functions. In some cases, objective function is static. In some, it's a dynamic. Some they use memory, some are memoryless, some use when they search single neighborhood, some use multiple neighborhood, and likewise. So you can, if you divide it into two common, most common division is trajectory and the population base. So in trajectory, all these methods are there, like local search, and you can see that they are not very, they are new. They are very old. Simulated aligning 1983, then taboo search, guided local, okay, iterative learning and all. And then there is a popular category of meta heuristic, that is population based. So all these things, they are like evolutionary programming, genetic algorithm 1975, and then ant colony 92, particle swarm 95, honeybee 2005, D 1995, and likewise. Most of them. So, and still people are developing a new every time. You'll find every day, or you'll search it, you'll find some either a totally new algorithm inspired from some species or some phenomenon occurring in the environment, or they are variants of it. Like PSO is inspired from the group behavior of the birds and all the species, but after that you'll find there are more than 400 or 500 variants of PSO. So those things are coming up. So let's understand what is trajectory based and what is population based. If you are planning to develop a new algorithm, it will help you a lot. So again, I'll try to connect all these algorithms on those three things: start, policy to move, and the stopping criteria. So trajectory, so it will randomly start from any point, say S0 here, and then what it will do, it will decide a region that okay, I'll in this region I'll see which are other solutions available. Randomly I pick a point. So in this region, randomly 1, 2, 3, 4, 5 points are taken, and then it will evaluate those. Once it evaluates, it will see that which one is better than S0 or which one is the best. That is policy. So suppose this one is best. So then around it, it will again take few points. Okay. And then again see which one is the best. And then likewise, it keep on moving. So this is a trajectory based method. Well, this one is easy. You can say very easy algorithm, but the problem is if any point is here or here, which is not in this circle, and maybe that is optimal, that will be skipped. So that is a disadvantage. Then people come out with another approach. So, okay, what is the local search? Let's talk about local search. This is the same what we talked about so far. So we take one point and then we put a band across it, both the sides. We evaluate and move. Say this one is better. So then we take this point, then again put a band, and then again evaluate and say this one is the next point. But now if we evaluate it on the both side of this red point here, both are giving higher value than this, and the algorithm stops. But we know that the best solution is here. That's the problem with this local search algorithm. Then people suggest that how to come out of this local search. There are various ways. They say that one of the ways, instead of starting with one point, start with multiple points. Well, this is a good way to do it. The second way is if it stops somewhere, like in this band, what you can do is you can perturb it, check it with a small perturbation on both the sides. And then if it is coming back to the same point, okay, then fine. If it is moving, so if I disturb it and it moves in this direction, and then I'll get another solution. Then I'll say, oh, this is going good. That is another way of doing it. Okay. The third way, they say that, oh, smoothen this surface. So all these things you will find, these are the methods people try to find it out to come out the problems of the local search. Okay, so some suggest like this, oscillate it, perturb it, okay, and then they worked on the various methods of perturbations to come out of the local traps and all those things there. Okay. So this one is sorry. Okay, let me give you idea here. Rest you can check it from the literature. So one way is whatever is there, add something to it. So it jump from here to this. This is one way. The second way is to move from this point to another point. Use the help of the neighboring values. So I have one neighbor here, another neighbor here. I'll see that this neighbor is doing what the value that my neighbor is getting. Based upon that, I'll move near to it, and likewise. The second method is the population-based method, and the population-based method is it's basically it starts some population with some population. So say this is the population. It's randomly take few points there. Okay, and then from this one, it move to the next more points. So going to the next more points, there is a policy that, okay, this is one population, how to go to the next population. And then out of this whole package, it will select which are the best. So it keep the best, discard the rest. And again, then go for the new population. And it keep on doing till it will reach to a certain kind of a minimum value and likewise. So these are the population-based methods. Okay. So they have certain advantage over earlier method, but you can see that since we are starting randomly every time, there are issues with this one. Okay. So one of the population-based method is genetic algorithm. So, okay. So how it works? The theory is it is inspired from our genetics. So we as a human are represented by a set of chromosomes. Okay, and that is our property as a human. So my chromosomes, and then I can check it, the chromosomes of my parent, there is a certain kind of a connection. So something is I'm carrying from my parents and then passing it to my children and likewise. So that is the one theory, one kind of formation. And then how the next population appear. There are few operations. So obviously from the parents, children will be there because of through a process of reproduction. So that we call here as a crossover. And when the children are there, children are not just a combination. They have something different also from their parents. We have observed extreme cases also. Parents are 5 feet children, boy or girl maybe boy maybe six, girl maybe 5, 6 or something like that. Or parents are not that intelligent, but the kid is very intelligent, and reverse way also. So that means something is happening there. So that we call it a mutation. And then there is natural selection, that is basically Darwin's theory, that is survival for the fittest. Those species who are fit to the environment, they survive. Those who are not fit, they will die out. So here the environment is our problem, optimization problem we are going to solve. So we use these three operations. So how it will work? So there are so many solutions. So we assume that any value in the constant environment is a solution. The only thing we need to find out what is the best solution. So all solutions we write in the encoded form, like 10101001. This is the representation of the variables. Like first 4 letters that represent one variable, the next 4 letters represent another variable, the next 3 letters represent the another variable. So number of variables you can put it into a string. So, and this represent one solution in the space. So if it is a 2 variable problem, it's a 2-dimensional space. If it is a 3 variable, it's a 3-dimensional space. If it's n variable, the problem is of n variable, it's a n-dimensional space. So each string represents a point in a space. Okay, so that is there. So what we will do is we take this set and then we consider 2 as a parent and we do the crossover. So this is one parent, this is another parent, and this line is known as crossover. Where we are doing a crossover, that is known as a crossover probability. And then there is a research. What should be there? Crossover probability should be low or it should be high. Very interesting things are there. If you check it, if I cross over here, then what will happen? And that means children, if I produce a children, there will be a very small change. Okay, if I do it here, maybe big change, and likewise. So there are studies that, but we represent it by crossover probability. And what will happen? It will take some features, some values from the first parent and some from the another parent and generate a one child. So all gray become one child, all white become another child. And then the second operation will take place, that is mutation. Mutation means randomly you can change anything anywhere. But where you are going to change it, change means if it is 0, you make it 1. If it is 1, you make it 0. Again, that is decided by the mutation probability. We put a probability and based upon that, this is decided. Once they are there, then what we can do it, now we have the children there. If children are there, then we'll not talk about this one, parents there. Then these are our solutions. We find out, we put these values into our function, get the values, and then we apply a survival for the fittest. Those who are fit, they will survive. Those who are not fit, they will not survive. So you can say, in a most simplest way, you just rank them according to the fitness, and you can remove the last one, replace with the best one. Likewise, there are many strategies there. And then those who survive, they become now the parent here, and this loop keep on working till you converges. This is a way of doing it. So what is the policy here? Start point, randomly. Policy to move is crossover, mutation, and selection. Stopping criteria is where you can fix it. You can go for 1,000 iterations, stop, that is a stopping criteria. Or you can say that, okay, if my answer best values are in this band, stop, then you can stop it. That is decided by the designer. This is how the genetic algorithm works. Well, let's move to the another one, which is basically, okay, let me check the time. Well, D is also a modified version of a differential modified version of genetic algorithm, but due to time constraint, I'll take another kind of variety here, which is particle swarm optimization. So what is particle swarm optimization? Again, the process is very simple. It is more of a group behavior. It is inspired from how we do the search. So let's say in a room, uh, if someone miss a gold coin, we have to search it. And the room is not a flat surface, it's an uneven surface. How we do it? So one thing is we randomly distribute. So this is how the thing started. They are randomly distributed. You can see at the top screen. And they say the coin is at this point, dark point. That is my optimal solution. So they randomly distributed and they start searching. So how we search? We start in searching in a certain direction. So you can see they are randomly distributed, all have arrows in different directions. So they randomly search it. And when we search it, so we take a movement. So now let's coming to, this is just two equation algorithm. Let's understand this part. When we do search, that means we have velocity. So I have initial velocity. Otherwise, if I don't have velocity, I cannot move. So this is my initial velocity. Okay. So I have initial velocity, take it from this graph, then we come to this equation. So I'm going in this direction. So I'll take one small step, go in this direction. When I reach here, I observe, no, that side the slope is more. There are more chances. So this is that direction. This is my preference, my best preference. That is this direction. I can see the slope. So I'll take a turn in this direction. When I take a turn and move a bit, then my friends, they say, no, this one is, here are more chances because this is more steep. Okay. So this one is my whole neighborhood, all my friends' preference. So I'll take a turn and then I reach to a new point. So initially I was here and this is the new point I reach, and keep on moving, searching in whole of the space. And finally you can see everybody reach to the solution. So it's a cooperative kind of a cooperative behavior algorithm. But how to mathematically you can design it? So see, you have initial velocity, you are in one direction, so this one is there. This is weighted one, we put a weighted parameter. Okay. The second one is I want to align with my best. So aligning my best means I want to go in that direction. Going in that direction means I'm reducing the distance between them, those 2 points. So that is what I'm putting here. My best, personal best, minus my current position. And then again, something is attached to it. We'll talk about these two things. But at this point, I want to move in the direction where my global people, everybody is saying that what is the best solution, that is best for us. So I want to reduce that difference also, that I put it. Now here the behavior comes into picture, that how much I want to give percentage to importance to my personal, and how much I give importance to my friend suggestions. So I put C1 and C2. If C1 is very high, that means I'm giving more importance to my personal decisions rather than my friend's suggestions. If my C2 is high, that means I'm giving more importance to what is suggestion coming from my friends. And we do these things every day in our life. Our decisions are always based upon three things: something which is coming from the past, some weightage to our choices that, oh, this is good, and some weightage to our friends what they are suggesting it. It's completely psychology, behavior analysis algorithm. Very nice algorithm. And then we are multiplying with random. Random because it's not always I give 50% importance to my personal choices. Sometimes 50, sometimes 40, sometimes 10. So that is basically randomness. Well, how it helps in mathematics? This randomness help in avoiding our local traps. So it helps in that perturbation I was talking about earlier. It helps us in moving yourself out of those local traps. This is how the velocity is updated. And then we know that velocity into time is the position. This is iterative algorithm. So every time iteration count is 1. So velocity into 1 is the new distance. This is the new one. And I add it to the old. I'll reach to a new point. There I'll again evaluate my algorithm and then keep on moving like this. So once I evaluate this algorithm, then I update these things because everybody is evaluating. So in next part, maybe this is also changed. I'll reach to a new point. My personal best may also change or may not be, it remains same. I reach to a new point and then I'll get a new velocity. And then this new velocity multiplied by time again added up. So it keep on moving and likewise, and it stops at a certain time and you have your solution. You can see there's no gradient here. These are gradient free methods. But again, the three things are common. First, starting, and that is randomly. In most of meta heuristic, we do it randomly. Okay. And the second, the policy to move. So these two equations are the policy to move. And stopping criteria, again, you can fix it. Okay. So this is another algorithm which is very popular, and later people have improvised on like uh, how to control C, how to control W, nature of W, and then starting point also. Many more things are there. Like W initially people started with fixed W, then they come out with the decaying W, then they come out stepwise decaying, logarithmic decaying, exponential decaying, and then some C and C1 and C2 function of something, and likewise. So all those are the variants of PSO. Okay, so I'll talk one more, and then I think then I'll take your questions. And this is ant colony optimization. This is inspired from ants. Okay, and I think you have seen it. This is the experiment. People have done it, but not like we have also when we were kids, we have also done it, but not exactly like this, but more like this. That we can see that ants are moving in a line, and then you put one obstacle there, and you'll find that ants distributed almost equally on both sides of it, and after some time they follow one path, and this path is the shortest one. Okay, so they are optimizing their path basically. Okay, and the theory is they are blind, so how they check it and all these things, that's very interesting part. So what is happening here? So when ant they move, they drop certain liquid that is known as a forminon, and they smell it. Now this forminon is basically it evaporates with time, and this proper time and temperature, this property is important. So you can see here only one ant forminon is there. The second one is smelling this forminon coming behind it, and more ants are there. So more forminon is there. Now once they distributed in these two sections, you can see here this section is taking a lot of time because it's lengthy. So the concentration of forminon will be less, and the concentration of forminon here will be more because it's a smaller one. So you'll find that after some time the ants start moving through this one, and the new one will find that more concentration in this path. So after some time everybody move through this path. That is the basically they observed it, and only this property they have used it for ant colony optimization. So they develop a forminon equations and then make the forminon equation as a function. Initially they say that there is a probability associated. They make the distance as a function of the concentration of the forminon, introduce the temperature also there, add some probability to it. and then the algorithm works that way. This one is more appropriate for path type of a problem, like congestion management, traffic management, and likewise. But the interesting part is it suits well there and perform very well in path planning problems and all those things. So again, the starting is random. They are started. The policy of movement is governed by these equations, which is basically the four concentrations and all that. Stopping criteria is again the same. You can make it fix it to some iterations, or you can say that my solution is in this band, stop it. If my solution is repeated 10 times, uh, then stop it or something like that. Okay, there are many such algorithms. Another one is harmony search that is inspired from the music formation. Just quickly, quick on this one, and then I'll take your questions. So we have instruments, and you know that some of the songs you still remember, some which you have maybe listened somewhere some when you were kids, and some songs which you listened yesterday but still not remember. So what is there? And that is basically the melody, which is a combination of the pitch and notes. So that is basically what we remember, and that is the theory here. Instruments and their pitch is they are the variables, and they have certain values. And these values, when you put it into the objective function, so whatever is giving me the minimum, that is the best solution, so that I keep it with me. And then how the pitch is varied and all those things. So what are the ways to develop music? There are various ways. Those are introduced here. So one, and this is really interesting for those who have some interest in music. You'll find uh, if you see, even listen some of the songs, you can easily recall who is the composer, because that is the way of composing here. What is uh, they try hit and try sometimes, and then one of the if one of the note or something is very popular, then what they do in future is they play near around it and produce second and third and one. So that is basically they are using the memory. So that comes here. That is harmony memory. They are using it. The second one is they listen it somewhere else in some other language, and then they improvise around a bit, and then they play with it. They compose a new song. That is the second way of doing. And third one is totally they are going for new. So those things are there which are being done here in various forms, like harmonic memory, that means coming from the memory, and pitch adjustment, you are varying the pitches, and then termination criteria. So this one is again inspired from the music and all that. Okay, friends, I'm stopping it here because the time is, I keep, there are so many algorithms here, but like all these things are there, but uh, today we are short of time in a way that keeping connecting both these two things is difficult. So I'm stopping my presentation, and now I'm open for the